Hello everyone. Today we are going to solve one problem to analyze bevel gears and design them. So we are solving this problem for bevel gears with 20-degree pressure angle. In this case, there is a pinion which is having 20 teeth and there is a second gear which is having 30 teeth. Then the module is 4 mm while face width is 20 mm. Material for both pinion and gear it is steel having ultimate strength of 750 megapascal or 750 Newton per mm square. These gear teeth they have been subjected to the process of grinding as well as lapping so that errors in the manufacturing can be reduced. Up to the class 3 they have been lapped. So because of that correspondingly there will be some error which will be obtained from the standard table. Then surface hardness value is 400 bhn. Pinion rotation speed is 500 rpm and it is actually receiving 2.5 kilowatt of power from electric motor. The starting torque is 150% of the rated torque, which means service factor has been provided to us. So we need to calculate factor of safety in bending failure as well as factor of safety in pitting failure. So this was the problem statement. Like our usual practice, first of all, we will write down the given things and then we will go ahead with the solution. So what are the given things? So the number of teeth on pinion, or actually, first of all, the pressure angle has been mentioned. So that is alpha is equal to 20 degree. Number of teeth on pinion, it is equal to 20. Number of teeth on gear, it is equal to 30. Module is 4 mm. Face width B, it is 20 mm. The value of SUT for both the cases of pinion and gear, it is 750 megapascal or it is 750 Newton per mm square. Both units are same. Then surface hardness value, it is BHN, it is 400. Then pinion rotation speed, so that is NP, it is equal to 500. The power which is being received from the electric motor is 2.5 kilowatt. Then service factor CS, because starting torque is 150% of rated torque, so 150%, this is what we have already learned, 150% per 100. So when you take this ratio you get CS value as 1.5. So now one more important input is that lapping and grinding, that process has been done. So there is this class 3, actually class 3 machining process has been carried out. So correspondingly we will have to determine the error while calculating the dynamic load. So first of all we need to understand some basics about the bevel gear. So the parameters, I will not explain everything, but the parameters which are necessary for the solution, they will be understood. So the parameter which we need is this pitch angle gamma, which is the ratio of number of teeth on pinion to the number of teeth on gear. It's tan inverse. So gamma we will be calculating, as well as we will be calculating this cone distance, because when we are talking about bending and when we are talking about pitting failure, these parameters will be necessary to calculate the beam strength and the wear strength. So let us proceed towards the solution. Just give me a second. So now let us proceed towards the solution. Okay, see, they have asked us about the factor of safety. What is the basic understanding that we always have? Let us say if we are talking about beam strength, then simple understanding is that beam strength should be greater than the P effective, the effective load which is coming on the gear tooth, which means if we want to replace this greater than sign with the help of equality sign, we need to introduce some coefficient. So SB should be equal to P effective multiplied by factor of safety. So if we determine SB, if we determine a P effective, then simply their ratio, it will give us this factor of safety. That's our objective. So we simply need to find out the SB. So the first understanding, the very first understanding that we have to develop is that in this case, both pinion and gear are made up of same material. They are made up of same material. So because of this, immediately we can write that pinion is weaker. So our design will be based on that. We have already solved one numerical in which there were two different materials for pinion and gear. You can go and check it out how we decided the weaker material or weaker component. In that case, that kind of numerical we have already solved. So in this case, pinion will be the weaker element than the gear. Then we will determine the pitch angle. That's what I said during explanation of geometry of the bevel gear, that we need to determine the pitch angle because it is necessary in so many steps. So now the pitch angle tan gamma, it is equal to Zp divided by Zg. So it implies that if I want gamma, then I will simply take tan inverse of this ratio, and I already have Zp and Zg. So number of teeth on pinion is 20, number of teeth on gear is 30. So gamma is tan inverse of this ratio. You can immediately calculate this. So this gives us that gamma will be equal to 33.69 degree. Okay, I think this ink has been, the brush has been selected wrongly. Fine. So this gamma is here with us, 33.69 degree. The next thing that we need to calculate, because we are talking about the beam strength here. So let me tell you the simple formula for beam strength in case of bevel gears. This SB will be simply equal to, let me just change the ink. Okay, so this SB will be equal to MB sigma B, then Y multiplied by 1 minus B by AO, that is cone distance, and that's why I showed you the cone distance in the previous step. So we need module, we need the face width, we need sigma B, which is SUT by 3, that is variable load, and then uh, finally this Y, which is Lewis form factor. Because this is a bevel gear and not a spur gear, so we will have to use the concept of virtual number of teeth to determine the value of Y, then again face width and the cone distance AO. So we will proceed with this. So ultimately, in this case, module is available, face width is given. So sigma B, that will be our next focus. So sigma B is SUT by 3. SUT, it was given as 750 megapascal. So SUT by 3, it is equal to 250 megapascal, 250 Newton per mm square. So our third parameter sigma B, it is also sorted. Now we have to proceed for the capital Y, that is Lewis form factor. Now I will simply write, just for your information, find Y using virtual number of teeth. So how do we evaluate the virtual number of teeth? That's the question. So that will be Z dash P. It will be equal to Zp divided by cos of gamma in case of bevel gear. So Zp, it is 20, that we already know. Then we have also calculated gamma just now, so that is 33.69 degree. So ultimately this ratio gives us Zp dash equal to 24.04. So this is as good as 24. And then in the previous numerical we have seen how to determine the Lewis form factor in case of different number of teeth. So in here right now what we can do, we can directly take this for this ZP dash equal to 24, the capital Y can be taken as 0.337. If this value of ZP dash would have been somewhere in between 24 and 25, or not very close to 24, not very close to 25, then we know that we could have used the expression of interpolation. This interpolation philosophy we have already studied in the previous numerical. So now we can go ahead with that. We can go ahead comfortably with this value of 24 and 0.337. So for 24 teeth, or I will simply write it like this, for ZP dash equal to 24, we can say that capital Y, it is equal to 0.337. This will not affect the accuracy much, but let us say if the value was something like 24.37, then definitely we would have gone for interpolation procedure. Right now we don't need this because it is very close to 24. So this capital Y is also there with us. The next parameter that we need is the A0. So it is the cone distance. I will just put it here. So A0 is given as square root of summation of dp2 by square, sorry, dp by 2 square plus dg by 2 square. Now dp and dg, these diameters are still not known to us. We will simply calculate them. So if we want dp, it will be equal to mzp, the pitch circle diameter. So ultimately that will be 4, that is your module, and number of teeth 20. So dp is 80 mm. Afterwards dg, it will be m zg, m is 4, and then zg is 30. So ultimately that gives us dg as 120 mm. Fine. So everything is now with us. So we can calculate this AO. So dp by 2, that is 80 by 2. So that is your 40 squared plus square of 120 by 2. So that gives us 60. So ultimately, when you calculate this in your calculator, you get A0 as 72.11 mm. So now you have all the parameters which are necessary to evaluate SB with the help of this expression, and that's why I wrote down this mother expression previously, so that our thought process becomes clear, the path becomes clear through which we have to walk and arrive at the solution. So ultimately, now let us solve this. So it implies that, once again I will put it here, SB is equal to MB sigma B y into 1 minus B by A0. Module is 4 mm, width 20 mm, sigma B is 750 by 3, so 250, capital Y 0.337 that we obtained from the table. 1 minus B is 20. A0 we have just calculated 72.11. So this complete expression you should put in the calculator and evaluate that SB comes out to be 4872.37 Newton. So now we have the beam strength, but we still do not have the P effective, and that's why I wrote down this basic equation first, that this should be our focal point. So we still do not have anything about the P effective, that we will proceed in that direction very soon. Now we can calculate the wear strength. Just give me a second, I will put it here. Now calculate wear strength. All right, so wear strength, again I will like to write down the mother formula, and once we determine the individual components, immediately solution can be achieved. So if you want wear strength in case of bevel gear, because it's not a complete teeth, some part of the teeth It does not participate in the process. It has been cut down. So because of that, the wear strength SW, it is given as 0.75 BQ dpk. So that is dpk upon, because of the presence of the pitch angle, upon cos of gamma. And that's why, like I said previously, gamma was necessary. So now here we have this B, we need to calculate Q, we have this dp, and we need to determine the K factor. So first of all, Q, which is your ratio factor, it is equal to 2zg upon, again this is not a spur gear, so it will not be 2zg upon zg plus zp, it will be 2zg upon zg plus zp tan of gamma. So that is equal to 2 multiplied by 30, we already have this, then again zg is 30, this is 20, then this will be tan of gamma 33.69 degree. You calculate this, then you will arrive at the conclusion that this Q is equal to 1.385. I should better be using some dark colors in here. I will just take a look at that afterwards. Okay, so this Q now we have, yes, Q is with us. K factor we have to determine. We already have the surface roughness value, the surface hardness value, and both the materials for both pinion and gear are same. So because of that, this capital K will be equal to 0.16 BHN upon 100 bracket squared. So that will be equal to 0.16. BHN value is 400 divided by 100 bracket square. So ultimately solving this, it gives you the value of K. I think this is too light. I will simply use a darker color. So ultimately the value of K, it will be equal to 2.56 megapascal. Again, the brush needs to be changed. Okay, so that is there. Okay, so the value of K is now also obtained with us. Fine. So now we can directly proceed with the calculation of SW. So that gives us 0.75. B is 20 mm. The value of Q we have just calculated, so that is 1.385. DP value we already have this 80 mm. Then K we just calculated that 2.56, and then divided by cos of gamma. So cos of which angle? So that is 33.69 degree. You please solve this in your calculator so that you can develop a proper understanding of this and perform well in the examination. So SW comes out to be 5113.53 Newton. Okay, so now you have the value of SW, you have the value of SB. So left hand side component of the equation is ready, because same understanding is here. This SW should be greater than the P effective. So every time P effective is the parameter which is troubling us, now we will proceed in that direction. So for that purpose, we will be needing the velocity. So we have been given that 2.5 kilowatt of power is being transmitted. So the torque which is transmitted because of this power, torque is given as mt, because we know if we want to transmit the power, it is equal to 2 pi n mt divided by 60 into 10 raised to 6. This is what is known to us. So if we are interested in mt here, we just have to rearrange the equation. So that gives us 60 into 10 raised to 6, 60 into 10 raised to 6 into kW divided by 2 pi n, because here we know the speed of piston and it is coupled with the motor, so it will be the rotational speed of the my mistake, not piston, pinion. So this is equal to 60 into 10 raised to 6 into kilowatt is 2.5. divided by 2 pi, and the rotational speed has been mentioned as 500 rpm. So when you solve this, you arrive at the solution that the value of mt, it is equal to 47746.48 Newton mm. Okay, so now we have this value of mt. Why this value will be necessary? Because this torque is being transmitted because there is a tangential force which is acting on the uh, gear tooth. So ultimately we can say that if we want that tangential force pt, it will be equal to 2 times mt upon dp, because conceptually speaking, whatever is the torque, it is equal to whatever is the force multiplied by the distance through which the force is acting. It is acting through the radius, so that's why dp by 2. So now you substitute the values, so what you get, mt is 47746.48 divided by the value of dp we have already calculated, it is 80 mm. So ultimately the value of pt that you can calculate as 1193.66 Newton. Now, why this component PT was necessary? Because we need to calculate the dynamic load using the Buckingham's equation, and that is why at that point of time the value of PT will be necessary. So now we have PT. The next thing that we need is the PD, which is the dynamic load. But for PD, we need the velocity. Just give me a second. Yes. Okay. So now we need to calculate the dynamic load. By Buckingham's equation. So what exactly is that expression? That expression is that if you want PD with the help of Buckingham's equation, the dynamic load, so it is equal to 21 multiplied by velocity v in the bracket CEV plus PD divided by 21v plus square root of CEB plus PT. So even if the formula is prolonged, but actually it is quite simplified, you just need to remember the proper arrangement of the uh, what we can say group of terms, CEB plus PT in the numerator as well as CEB plus PT in the denominator, 21V in the numerator, 21V in the denominator. So the value of C, it is conveniently taken as 11,400. So that is available with us. Now, our most important focus point in this case is the determination of this error, small e. So this small e, the error which is there, it is because there is some machining operation which has been carried out while manufacturing the gear. So what I will do, I will just do this parallelly. So velocity v, if we want v, then it will be equal to translating this rotational speed into the linear velocity. So pi dp np upon 60 into 10 raised to 3, because we want to have the velocity in the meter per second unit. So pi dp is 80 mm, np, the rotational speed of the pinion, is 500 mm divided by 60 into 10 raised to 3. So we now have the velocity as 2.094 meter per second. So this velocity, it has been sorted. Then we already have the parameter b, so we don't need to worry about it. Just now we have calculated the pt. Now about error e. So for this purpose, we have to refer this particular table, which gives us the maximum expected error between the two machine teeth, and for different machining operations or different categories or different classes, errors have been specified. So in this case, our module is 4 mm. That's the first input which is necessary to obtain the value from the table. So we input the module here. Yes, it is up to 4 mm. Yes. And the machining in the problem statement, it has been told that the uh, component has been lapped and ground up to the class 3. So that's why when we refer to the class 3 for module equal to 4 mm, we get the maximum expected error as 0.0125 mm. So ultimately we will be using this value. So ultimately our value of E is 0.0125 mm. This has been sorted. Now we can proceed towards the solution. So now we have all the necessary entities. So that gives us 21 into velocity v 2.094 multiplied by, in the bracket, remember capital C, it is equal to 11,400 Newton per mm square. Okay, so 11,400 Newton per mm square multiplied by 0.0125. I think I should take this out. Yes, 125, and then multiplied by 20 plus the value of PT is known to us 1193, just we have calculated that 0.66. Okay, so numerator is set. Now we can set up the denominator. So again 21v, 21 multiplied by 2.094, my mistake. So then plus square root of CEB. So C is 11,400, E is 0.0125, B is 20 mm, plus PT is 1193.66. Remember, you have to take the square root of this entire term, CEB plus PT. So once that square root has been obtained, you have to add it with the product of 21 into 2.094. So now when you solve this, it is not a difficult term actually, once you understand that there is a similarity between the numerator and the denominator. So that's how you keep these many formulae in mind. You don't need to mug it up, you just have to understand them. So now PD, when we calculate all of these terms, put it carefully in the calculator. Accuracy is more important than speed. So once you achieve the accuracy, speed will automatically follow. So now the PD value is 1653.25 Newton. So that is 1653.25 Newton. That is PD. So now you have PT as well as PD. Then simply, if you want the P effective using the Buckingham's equation, then ultimately, just give me a second, I will change the ink. Yes. So it implies that if we want the effective load, because we have used Buckingham's equation, so effective load P effective is equal to CSPT plus PD. It's that simple formula, and we have everything which is necessary to solve this formula. So ultimately this CS, it is 1.5, PT is 1193.66 if I'm not wrong. Yes, 1193.66 plus PD that we just calculated 1653.25. You put this in the calculator and find out that effective load on the gear tooth, the parameter for which we have done all this exercise, that P effective is 3443.74. 3443.74 Newton. So now, with the help of that very small understanding that SW should be greater than P effective or SB should be greater than P effective, on the basis of that very small understanding, we have arrived up to this solution. So SB, it will be equal to P effective multiplied by Fs. Also SW, it should be P effective multiplied by Fs. Remember, nature of the strengths is different, and that's why value of Fs, the factor of safety, it will be different. Just give me a second. Okay, so the value of SB, then ultimately if we want in, sorry, in bending, and this is in pitting failure or the wear failure. Okay, so ultimately if we want it in bending, then Fs will be equal to SB upon P effective. The value of SB we have already calculated, that is 4872.37 divided by P effective we just calculated 3443.74. So ultimately the value of Fs, factor of safety in bending, is 1.41. That is your first major answer. The second major answer is again simple. So if I want factor of safety in wear or pitting failure, then at that point it will be equal to simple rearrangement of the terms, SW upon P effective. So SW we have already calculated. SW is 5113.53 divided by P effective 3443.74. So ultimately factor of safety in case of wear failure or pitting failure, it will be equal to 1.48. So please remember that we have not done very complicated mathematics. We have used this simple understanding, and we have broken down everything into its individual components, so that even if it seems that you have performed these many calculations, but still the basic understanding has been very simple, that you have to follow this relation, this basic understanding, and then accordingly things can be modified whenever there is modification of gear tooth. So I hope this video or this numerical is helpful to you. It helps you to, most importantly, develop the understanding about the problem solution methodology or thought process. Thank you.